Let's talk about KV cache optimization. If you've ever worked with large language models in production, you've almost certainly run into the KV cache, either as the thing that makes your system fast or the thing that quietly destroys your memory budget at 3 in the morning. Understanding it deeply, not just knowing it exists, but knowing exactly how it behaves under pressure, is one of those things that separates engineers who can architect real AI systems from engineers who are mostly guessing. So what is the KV cache? When a transformer model processes a sequence of tokens, each layer computes 3 things for every token: a query, a key, and a value. The attention mechanism then uses those keys and values from all previous tokens to compute what the current token should attend to. Here's the insight that makes the KV cache valuable. If you're generating tokens one at a time, the keys and values for every token you've already processed are not going to change. They're deterministic given the model weights and the input. So instead of recomputing them on every single forward pass, you store them. You cache them. That's the KV cache. It trades memory for compute, and in almost every production setting, that's a trade you want to take. The savings are dramatic. Without a cache, generating a 1,000 token response from a prompt of 2,000 tokens means you're doing roughly 3,000 tokens worth of attention computation on the very last step alone. With the cache, each new token only needs to run a single row of new key value pairs through the attention layers, and everything else is just a lookup. Generation goes from quadratic to linear in time. That is not a minor optimization. That is the difference between a system that responds in 2 seconds and one that responds in 2 minutes. Now, let's get into where it gets hard, which is everything after that basic definition. The first problem is memory. A single key value pair for one token in one layer is a tensor of size 2 times the number of attention heads times the head dimension, stored in float 16. For a large model like Llama 70B, that's on the order of half a megabyte per token per layer, and there are 80 layers. Run the math. A single request with a 4,000 token context might need over a gigabyte of GPU memory just for its KV cache. Run 30 concurrent requests, and you've consumed your entire A100 before the model weights even show up. This is why memory management for the KV cache is one of the defining challenges of LLM serving infrastructure. The solution the field has converged on is called PagedAttention, which is what powers VLLM. The key idea, borrowed directly from virtual memory and operating systems, is that you don't allocate KV cache memory contiguously or eagerly. Instead, you divide GPU memory into fixed size blocks, called pages, and you allocate them on demand as a request grows. Different requests can share pages for common prefixes. You can swap pages to CPU memory when GPU is tight. You can even copy on write when 2 requests diverge from a shared prefix. This turns KV cache memory from a rigid, wasteful pre-allocation into a dynamic, shared pool. The throughput improvements in practice are often 3 to 5 times compared to naive implementations. Prefix caching takes this further. If you're running a system where many requests share a long common prefix, think a system prompt, a document that gets